Hi, I'm Duncan Pearson. I'm Chief Architect of Anaplan. Been at the company just over 4.5 years, and I'm responsible for the design of the Anaplan system, both now and into the future. With that, Anaplanners, ask me anything. Community member Bradley Sisson has asked a question about how the calculation engine works, in particular to help in understanding how to design with performance in mind. Now, a full explanation of how the calculation engine works would be far too long for this session. So what I've done is I've added a link to a video that's on YouTube that gives an explanation. It's about an hour long. But what I will say here is designing for performance is a really important thing. And it's very easy when you start to, say, convert a spreadsheet model into Anaplan, or take some requirements for a system from some people, to build a model that does functionally what you need. But when you scale it up for maybe 500 people all contributing at the same time, with the scale of data that's in your system, you'll find that it doesn't perform very well. Anaplan is no different from any other system in that when you build an application with it, you have to take into account the scale and the usage of that application in the design right from the start. So, have a look at the video, take the lessons, and then use those in your designs. Community member Edgar Gomez has asked a question about whether it's possible to write calculations to optimize parallel execution. And it's not always simple to determine whether this is a good idea or not. So, I have an example and a number of slides. Here we have a standard margin percent calculation, where margin percent is calculated from profit, and profit itself is calculated from cost of goods sold and revenue. Now, in this example, each calculated line item uses one operation per cell to calculate from its dependent line items. So for each cell of margin percent, there are 4 operations, one for each line item. However, if you look at the way in which they're calculated, because you can't calculate profit before you've calculated revenue and cost of goods sold, and you can't calculate margin percent until you've calculated profit, the calculations need to be done in 3 waves. There's another way of writing the calculations in which each of the calculated items depends only on the primary data, those 3 line items: sales volume, price, and unit cost. And you can see the calculations are more complicated, and in particular, the calculations do more operations each. To calculate margin percent in this case, and the others, we are doing not the 4 calculations, but 7 this time. So you'd think that that would be more efficient, more inefficient. However, if you look at the sequence of the calculations, you'll find that each of those calculations can be done alongside the others. They can be executed in parallel. And one of the things about the way the Anaplan calculation engine works is that as it calculates the consequences of any change, or as it does the full calculation of the line items when the model loads, it has 144 threads to do those calculations. And anything that is independent is done in parallel. That means that a change to any of these primary line items would get executed more quickly in this case than in the other case. Another example of this is when we look at time, and in particular the accumulate function. So the data in Anaplan is divided into blocks, and if it weren't for time, then it would be one block of data per line item. However, there are certain calculations to do with time, like opening balances and closing balances, where that would result in circular calculations. And as you know, you can't have circular calculations within Anaplan. So what we do is we divide the data up into one block per time period. And that means that what was previously a circular calculation can then become a spiral calculation. Now, with one block per time period, if you look at the way Cumulate works, each block of a Cumulate result depends on all the previous blocks of its source line item. And so the first block of the result only takes one read and no additions. The fifth block in this example, it has to read and add together all 5 previous blocks of the source line item. Okay? So that's 15 read operations and 15 additions, but it is only one wave of calculations because each of the time period blocks of the target are independent. They can be executed together. So there is another more efficient way of doing this calculation, and that is to use previous. And you can see from this, if you, instead of using Cumulate, use the sum of the previous value of the target line item and the corresponding time period of the source line item, then it's very many fewer read operations and very many fewer additions to get the same result at the 5th period. However, the operations that it does have to be done in sequence. So it can't do the 2nd period before it's done the 1st period, and so on. And so you'd think that Cumulate was, despite being less efficient, was the quicker way of doing these calculations. But it all depends on the scale, and in particular, how many periods there are in the time period. So in the time scale, if, for instance, we only have 1 year and it's in months, then you can see the Cumulate only is 6 times more operations than the previous method. And the parallelism of it, in that case, will outweigh the inefficiency. But if, for instance, you go to a 4-year timescale and it's in days, you can see that Cumulate is doing 500 times more work than the equivalent previous. And that means that no matter how parallel you make it, it's going to be slower. So this illustrates one interesting characteristic of Anaplan. No matter what lesson there is to learn, typically it all depends on various factors of your model. So one of the things I would say is, if you have something where you can use 2 different methods and each of them has advantages and disadvantages, try it out in your model at the scale that your model is going to be working. So there is one further complication, and that is that if any of the blocks are large, then the calculation of them is split into subtasks. Because none of the cells depend on any of the other cells in the blocks, then these subtasks can be done in parallel. And what happens is, if there are more than 200,000 cells in a block, it's split into these subtasks, and each of the subtasks is no smaller than 100,000 cells. That means that if you have 1 million cells in a block, that's going to divide into 100 subtasks. And that is enough to get all the parallelism you're going to need. Community member Edgar Gomez asked another question. He asked whether sparsity affects performance as well as it affects the scale of a model. And the simple answer is yes. This is because regardless of whether any part of a line item or module has data, we still calculate the values from it. This means that it's doubly important when you're designing a system to identify those parts that you absolutely need to be calculated and design modules around those, and then take other parts of the system that perhaps are not used as frequently, and you can design them in a different way to be less sparse. So for instance, if you have an account hierarchy and only 10% of that account hierarchy is in use in this year, and you're doing sales forecasting, for instance, then do your sales forecasting on that 10% in a multidimensional cube, but keep the other 90% of obsolete products in a tabular form using a numbered list. Edgar's next question was about whether to use properties or line items. Now, structurally, a property of a list is the same as a line item of a module that only has that list as its dimension. And people often ask, is there any difference in performance between the two? And technically there isn't. The performance of a property and the performance of a line item are identical. However, I would recommend that wherever you can, you use line items in modules rather than properties. There are a number of reasons. So, first of all, you have the model map that shows you all the data of the system, but it only shows you the modules and the line items within the modules. So, if you use a line item, then it will show up in the model map. Also, on line items, you can set a summary method, and that means that if the list has hierarchy with multiple levels, you get data at the higher levels as well. Whereas with a property, it's as if the summary method was none all the time. And finally, there's a lot better support for things like filtering in views and formula editing for line items. Community member Edgar Gomez asked whether the number of hierarchies makes a difference to performance. I'm going to assume that this means the number of hierarchies on a module, and I hope that that's the right assumption. So, if you look at a module with, say, sales volume with 3 hierarchies on it, and those hierarchies have perhaps 2, 3, and 4 levels each, including the top level, as in the picture with region, product, and channel hierarchy, then for the line items in that module that have a summary method, and that tends to be most of them, we calculate in advance and we keep up to date all combinations of the levels of those hierarchies. So if you look at the leaf data, the skew by city by channel data, that's one block. But if you look at the aggregations of that, then that is 23 more blocks of data. And we have to calculate all of those and keep them up to date. Which means that every time you change a cell, then that change has to ripple through all 23 other blocks. Now, if you don't need those, if you're not actually using any of those summary blocks, if you're not reading any of the aggregate data, that means it really does make sense to turn off the summary method, and you'll save not just the data, the space for the data, but you'll also save time when the leaf data is being updated. So another aspect of the levels of a hierarchy is that it actually makes a difference how many levels you have. And in particular, a large hierarchy with only a top-level item is potentially quite inefficient. And I'll explain why. On the left, we see the standard city, country, region, all regions roll-up. Now, if you change city number 5, and its parent is country number 2, then in order to recalculate country number 2, it's going to read from city 5 and city 4. And in order to recalculate region number 1, it's going to read from country number 3 and country number 2, and so on up the chain. Now, in this case, that would only be 7 reads and additions in order to recalculate the top level all regions. But if we took out those middle 2 hierarchies, then see what happens. When I change city number 5, in order to calculate the all region number, I have to read from every single city of that hierarchy. And in this case, where we only have 10, that may not be too significant. But if your hierarchy is 50 million items, then that's adding up 50 million numbers every time you change one of them. Now, in that case, with 50 million, what I would do is I would create an artificial level in that hierarchy of, say, 7,000 members, which is roughly the square root of 50 million, and arbitrarily assign the cities to those members of that middle level. Then, whenever you make a change to a single city, then that's only adding up 2 times 7,000, 14,000 items, instead of the whole 50 million. And you can see that that would make a huge difference to the speed of recalculation. Looking at the left-hand side, you can see why it's important for Anaplan to hold in memory the results of all the aggregations. You can see that if we hadn't held the results of the region aggregation and the country aggregation in memory, then we wouldn't be able to use those results in calculating the individual modified items in those levels as part of going up to calculate the top level all regions number. Community member Evan Townsend asked a question about how you can make calculation utilities work for different users who want to use them with different parameters. Now, if you have a calculation in the model and you want a user to enter parameters that affect the way that calculation works, then that calculation has to be working on data specific to that user. Because if another user at the same time is entering their own parameters, then the calculation needs to be run in parallel for that other user. So we put a feature in the product, I think it was about a year ago, which is the user list. So the users that you see on the Users tab of the model now appear as a list that you can use in a module. And in particular, you can use that as a list in a module that holds the preferences that those users, the parameters that those users want to use in the function. What it does mean is that any of the parts of the calculation that that utility needs to operate on will need to have that user list in its applies to, and this can increase the scale of the model. But one characteristic of the users list is that each individual user only sees the parameters that apply to them, and they only see the results that apply to them. This means that to the user, it appears as though they're the one controlling those parameters within the model, but other users are completely invisible to them. So Anaplan is very flexible, and quite often you can achieve a particular result in a number of different ways. And many times, the way that you will choose will depend on the kind of systems that you've used before. And one of the characteristics of Excel, which often people use to build models and then convert to Anaplan, is that in order to handle multidimensionality, you have to do an awful lot of building of compound keys using strings, and then calculations on those strings to do aggregations. Now, taking that kind of model and moving it to Anaplan has quite a significant effect. So if we look here at different data types, what I've done is I've done some tests, and these are the results of doing particular operations on different data types. So we have 6 basic data types in Anaplan. The Boolean, which is true or false value, the list, which is members of a list, time period, dates, normal numbers, and text strings. And if you look at this graph, you can see that reading a value from a text string is marginally more expensive than it is from any of these other data types. When we look at the modification performance, it is very much more marked. So here we have adding 1 to a number doing a not on a Boolean value, similar things for the other data types, and adding one character to a string. And you can tell here, the modification of the string takes 50 times as long as the modification of any of the other values. And so if you have a model which is primarily using string calculations to do its logic work, it will run very slowly. If you can do calculations using Booleans and using aggregations of those, then do that rather than using strings. And one of the features of the strings is that we have a particular function called text list. And that allows you to do aggregation of the non-blank values in that text string up to a higher level. So it produces a string which is the concatenation of all the values below it in the hierarchy. Now, if you use that, and then someone changes a value in one of the underlying cells, it has to regenerate that entire text list. Because we cannot modify a string in place. Java doesn't allow that, which is that Java's the language we use for our implementation. So as it does that recalculation of that top-level string, it uses a mechanism that allocates and then throws away up to twice as much memory as is actually used in the string. And then we throw away the previous value of the string, which could be megabytes of data, and replace it with the existing one. And that will happen every single time that you modify any value that feeds into it. And what that does is it produces what we call garbage. This is memory that is no longer being used, but which the Java virtual machine in which the Anaplan calculation engine is implemented has to collect, and it has to process it and get rid of it. And that takes a lot of time. So that actually has as much effect, if not more, on the performance of your system than just the general extra time that the modification of those strings takes. So, anytime you can avoid using strings and do a calculation using any other data types, then do so. Community member David Smith asked me what I am most proud of in my time at Anaplan. So, I knew Michael, our founder, before he left our previous employment and started off by himself and spent 2 years in a barn writing the seeds of what would become this Anaplan system. And I can truly say that I am most proud of being part of this fantastic organization that has taken this amazing piece of software that Michael wrote and turned it into a planning system that is helping thousands of people in hundreds of companies to plan better. Community members Ann Cooper, A. Black, and Mark Shamaria all asked very similar questions about what we can expect to see in the future, and in particular the direction that planning is heading. So one of the things that we're focusing on is handling of sparsity. We are looking at ways in which we hold the data in memory so that we can retain that characteristic of having the aggregate and calculated data there and keeping it up to date, while not taking up so much space to do it. We're also looking at distributing the work of holding and recalculating a model over multiple machines so that we can hold much larger models and that we can spread the work of the individual users across our whole estate. Another way that we're looking into the future is at how you build models, and in particular how we can help by delivering content that you can use in your models. And this is at a slightly finer grain than, for instance, you might see in the App Hub at the moment, where you can go to a model and it's a very good representative of how to use Anaplan, but you can't use part of it in your own model. So the direction that I would like to take us is where we have individual lists, individual types of things individual measures with their associated calculations, perhaps, as units within a library that you can compile together to build your model. And that's not to say that you wouldn't be able to configure things once you'd brought them in, because we know that one of the key selling factors of Anaplan is its flexibility to handle your particular problems. And this refers back to the question that Evan Townsend asked. He asked about calculators. And one of the things that I would like to see, and it's fairly difficult, so we're not going to see it anytime soon, is the ability for an Anaplan modeler to define a calculation in Anaplan using standard modeling mechanisms, and then to encapsulate it and to give it a name in such a way that they could actually use it in a calculation in the same way that you use a normal function. And so that would give the ability to extend the Anaplan calculation language with calculations built using Anaplan. Finally, Mark Shamaria asked about where we're heading in the long term. And I can give you my opinion of that. I can give you where I would like to see Anaplan, because I think perhaps I am actually very ambitious. I would like to see Anaplan as being the technology that sits behind the making, the communication, and the maintenance of every forward-looking decision, not just in the enterprise, but in the world. Thank you for participating in Ask Me Anything. Please visit Community and see what's coming up next, and also take part in the survey and tell us what you thought.